You may notice as you look through sections of the book that the initial truss examples are relatively simple with just a few truss members and joints, but they get progressively more complicated as we get further into the chapter. It is not unusual for actual trusses to be comprised of hundreds of members and joints. For this reason, it's helpful to be able to identify members that enable us to simplify our analysis. Zero force members, like member BD of example 1 in the first part of our presentation, are members that carry no load and can help simplify our analysis. You may wonder what utility a zero force member has if it isn't carrying any load. Isn't the point of truss members to distribute load? If it isn't carrying a load, why not just get rid of it? These are legitimate questions, but it turns out that a zero force member can still perform an important function even if it isn't carrying load itself. We'll get to that later. For now, we'll identify conditions that permit us to identify a member as a zero force member. Consider the joint connecting members AB, AC, and AD shown below. Two of the members, AB and AD, are collinear. No load is applied at A. Using an XY coordinate system with the x-axis aligned with the two collinear members, y-component equilibrium tells us that the load AC is 0. This is the case unless the angle alpha takes on special values we are unlikely to encounter in a truss. Member AC carries no load and is therefore a zero force member. Now consider the same joint with an external load P applied at A. Y-component equilibrium now tells us the force carried by AC is non-zero, except for the special case where P is applied in the x direction. Assuming P is applied in the y direction, that is, the non-collinear direction, as shown in the figure, or at least has some non-zero y component, member AC is not a zero force member. Identification of a member as a zero force member involves examining joints and the number and configuration of members connected at that joint. This slide summarizes criteria for three members coming together, which is a common situation we'll encounter in trusses. As the slide indicates, the non-collinear member of a three-member joint can be identified as a zero force member if two of the three truss members are collinear, the x direction in the figure. There is no external force component at the joint in the direction normal to the collinear direction, the y direction in the figure. Under these circumstances, equilibrium in the direction normal to the collinear direction requires the non-collinear member to carry no load and therefore be a zero force member. Zero force members may also present themselves in circumstances involving other combinations of members. If we return to example 1 of the first part of our presentation, a free body diagram of joint D looked something like this. Here we had joint D, and we had a reaction force here, dy, and then we had loads carried by member FDE, and we had member FBD. And it may not be clear from this little sketch, but these are mutually orthogonal. Here only two members are coming together, BD and DE, but the reaction at D functions as a third member bringing a load into the joint. Here the reaction force and member DE are collinear, and member BD is therefore a zero force member. More generally, if we have a portion of a truss that contains a joint connecting just two non-collinear members with no external load applied at that joint, equilibrium of the joint tells us immediately that both members carry no load. So suppose I have a situation like this. I'm going to call this joint A, and that's going to ultimately be the focus of my attention. So here, let's say this is part of a truss. Where I have these joints B and C, And we'll just note here, here's a joint A. It has two non-collinear members coming together, and there's no external load applied at that joint. Okay, we'll call, just to have, again, be consistent here with our previous treatment, we'll call this angle alpha, and we'll establish an XY coordinate system like this. Okay, so if we write our force component equilibrium equations here based on a free body diagram of A, let's see, our free body diagram of A, I should say first, we should actually sketch that out. Here we're going to have FAB, and here is FAC. Here's this angle alpha here. And so again, based on that coordinate system, if I write some of the forces in y equals 0, I'm going to have simply FAB sine alpha is 0. And so therefore FAB is equal to 0 again. And if I write some of the forces in the x direction equal to 0, I'm going to have minus FAB cosine alpha minus FAC is 0. But since we've already established from y equilibrium that FAB is 0, FAC is also 0. So again, here's a situation where we have two members coming together, two non-collinear members coming together with no external load, and equilibrium tells us immediately that both of those members are zero force members. Suppose now we have a configuration that looks something like this. And we'll call these A, B, C, and D. And my interest now is going to be at this joint here at C, where we've got four members coming together. We generally can't make a statement about zero force members under these circumstances. However, sometimes it will be the case that one of the non-collinear members has already been identified as a zero force member from the examination of a different joint. In this case, BC will already have been identified as a zero force member from an examination of joint B. Then, from the perspective of applying equilibrium to joint C, it is as though member BC isn't there. Even if it is physically present, the fact that it carries no load means that the current four-member joint looks like a three-member joint, and we can again identify the remaining non-collinear member, in this case CD, as a zero force member. We'll take a look at an example now. Example 2 shows a truss with 21 members and 12 joints. This is clearly an example where it would help to identify zero force members before we proceed further. As we scan the truss, our first impulse should be to look for joints involving three members, two of which are collinear with no external load applied to the joint. Two locations jump out at us. Joints C and K, where BC and JK are identified as zero force members. To determine if there are any other zero force members, re-sketch the truss with the previously identified zero force members removed, or just crosshatch out the zero force members as they have no impact on equilibrium. Then repeat the exercise of scanning the truss for joints connecting 3 members, 2 of which are collinear with no external load applied at the joint. Joint B then becomes of interest. BE is the non-collinear member, and it must also be a zero-force member. Here is an example of joints involving 4 members coming together, but the results of a previous analysis had identified BC as being a zero-force member. So from an equilibrium perspective, joint B looks like a connection between collinear members AB and BD and non-collinear member BE. Our 3-member joint criteria are again satisfied, and BE is a zero-force member. Note that we can't make a similar statement about member IJ because the vertical force applied at J has a component in the non-collinear direction, that is, in the direction normal to members HJ and JL. Cross-hatching out member BE, we repeat the exercise of scanning the truss to see if any new zero-force members present themselves. But no others are present, so the zero-force members are just those sketched as dashed purple lines. A couple of additional points about this exercise merit discussion. First, note that we have not only identified 3 members as zero-force members, but equilibrium in the collinear direction at joints C, B, and K tell us the load carried by CE is the same as the load carried by AC. The load carried by BD is the same as the load carried by AB. And the load carried by IK is the same as the load carried by KL. In fact, even though there are no additional zero-force members, we can take this one step further and note that equilibrium of joint E tells us that EG carries the same load as CE, and member DE is carrying a tensile force equal to the load applied at E. If we begin this problem by finding the reactions it supports A and L, and then apply equilibrium to joints A and L, we will have determined the loads carried by 12 of the 21 members of the truss with relatively little effort. Hence, the value of identifying zero-force members is not just in identifying the members themselves, but in simplifying the analysis of the rest of the truss. Second, it is tempting to look at loading like this and focus initially on a joint like J. Here your impulse may be to say, how can a vertical load applied at J not result in member JK taking some portion of that load? But equilibrium of joint J only provides 2 constraints, force component equilibrium on 4 members. That doesn't provide enough information to tell us how much load JK takes, even if the figure makes it look like JK must be taking some of that load. Here it is important to remember that every part of the structure must be in equilibrium simultaneously. Equilibrium of every joint, every section, and the structure as a whole must be ensured. In this case, equilibrium of joint K is providing a definitive statement that JK is unable to carry any load, so it doesn't matter what the figure looks like. In this case, all of the non-collinear portion of the load applied at J must be taken by IJ, with the load in JH determined by the collinear equilibrium equation at J and knowledge of the load taken by JL. We now take a look at an example where we can use what we've learned to identify the loads carried by truss members as simply and efficiently as possible.